Hello, and welcome to Team 268 Robotics FRC CAD tutorials. In today's lesson, we're going to be diving deeper into constraints and using them to assemble FRC VEX parts. In addition, we're going to be going over some more important CAD skills that will be necessary for using CAD for FRC.
So before we go over what Lydia's about to go over, I'm going to reiterate what we said in assignment number 4 on basically how to move parts into your folder on the server and then import them into the assembly and then finally save the assembly. So let's say we want to make our screen look like this, right? So as you learned in lesson 5A, this is a corner gusset and this is a bearing. So first off, go into the server folder and then go to your folder for that assignment. So CAD shenanigans, summer people, and I'll just use Alice as an example, right? So assignment number 5, and here's your folder right here. So just leave this window open for now. Now make a new File Explorer window. And then you're going to want to go into the CAD shenanigans folder and then go to the parts library. So basically, this is where we have all of our different parts that we're going to use for CADing. So these are all VexPro parts, and they were downloaded from VexPro's website, and we will go over that at the end of this lesson. And they're all in here for you, so you guys can just use them, right? So you saw how we need, right, a corner gusset and then a bearing. So if you go to Gussets, and then corner gusset, just right-click, copy, and then paste it into your folder for that assignment. Next, we'll go get the bearing. So go back to the parts library, click bearings, and then we want a 0.5-inch flanged hex bearing. So right-click, copy, and then paste that into your folder. So now that we got the two parts, we're going to want to start an assembly. So go back to Inventor, click New, New, and then standard.iam, click Create. And before we actually put anything into the assembly, we're going to save it first. So again, currently there's some problems saving things directly to the server the first time you save them, and we're trying to fix that issue right now, but for the meantime, do File, Save As, and then just save it anywhere that's not on the server. So I'll just save it to my desktop. So you can rename it number 5 or anything else you want. Click Save. If this pops up, just click Yes. And then close out of this tab right here of your assembly. Go back to File Explorer. I would just make a new window. Go to the desktop. Move that number 5 into your folder as well. And now open it. So now we're working off the server, and now when you save it, it will be okay. So to place the parts, if you remember from lesson number 4, you click Place, and then you go to your folder where we just copied the parts. And the reason why, by the way, that we don't just paste parts directly from the parts library is because when you do that, it can sometimes mess things up, or you can accidentally make a change to the part and then save it back there and overwrite it. And if everyone does that, it's going to affect everyone's project. So that's why we transfer the parts first from the parts library into your folder, and then you can place them from your folder into the assembly. So again, go to your folder. So Alice, number 5, and then we can place the corner gusset first. And then we can place the bearing second. Or you could do it the other way around, doesn't really matter. So go back to your folder. Summer people, Alice, number 5. And then put the bearing in. So now we've got our two parts. That looks like pretty much what we have here. And finally, to save the assembly, just click the Save button on top. And then this will always pop up usually. Just click yes to all and then click OK. And so once it's done loading, it should be saved. And now just, if you want to copy any more parts into your assembly, just remember, copy them first to your folder from the parts library, and then place them from your folder, not from the parts library. And just one other FYI, and this will be helpful with assignment number 5, and you'll see when you look at the resources that we give on the website, is you can actually place assemblies into other assemblies. So if you click place, I can't place this one in because you can't place an assembly into itself, but if I go to some random other assembly we have, like, I'll just find something from last year really quickly. Past years. So if I place the hatch intake from last year into this assembly, so you can see here how we have this assembly, and if you click your button, it will basically just place the assembly within the assembly. And you can do this for as many assemblies as you want. Like, for example, if you save this assembly right here and then make a new assembly and put other parts, and then you can also place this assembly in that assembly. So you can basically do whatever you want, and that becomes very useful when you start working with large components, as you'll see when you do assignment number 6 as well. So just keep that in mind. That's something that we did not mention in the last lesson. And just one other thing I want to mention really quickly is I recommend that you follow along with all of these different constraints that Lydia's about to go over, because these are super duper important, like really important for pretty much everything going forward and pretty much everything we do in FRC during the build season. And everything you learned before in the previous lessons are also very important, but this builds on top of everything, and this is really what we do during the build season, is importing these parts, placing them, and then assembling them together.
A very common constraint in CAD involves circular objects and circular holes. In this scenario, we have a bearing and a corner gusset, and we're going to try to put this bearing into the bearing hole of the corner gusset. So we'll select Constrain, and for our first selection, we're going to hover our mouse over the curved bottom surface of the bearing so that this green line or green arrow appears. Notice, make sure when you hover over the bearing that a green dot is not appearing, but rather a green arrow. And when the green arrow appears, click it to make your first selection. And for the second selection, again, hover your mouse over the curved surface of the hole, not so that a green dot appears, but so that a green arrow appears, and make your second selection. You'll notice that our solutions are a bit different. We have opposed, aligned, and undirected. These solutions basically tell how the green lines or the green axes of our curved components should line up. For opposed, if I select that, you'll notice that the bearing switches direction, and that the green lines, which are actually arrows, the arrowheads point in opposite directions. They're opposed. If I select align, the arrows point in the same direction. And if I select undirected, it basically means that I am indifferent to how the axes point relative to each other. So I'm going to click apply, and you'll notice that when I try to pull the bearing out now, it always stays aligned with the hole. For our final constraint, we're going to select Constrain, and we're going to select the bottom lip of the bearing, and for our second selection, we're going to select the surface of the gusset, and after we click apply, now the bearing sits in the hole comfortably, and it will not fall out. Another common constraint in FRC CAD is constraining anything to fit into a hex hole. For instance, putting this hex shaft into this hex bearing. Our first constraint is going to be a mate. So for our first selection, we'll select any hexagonal side of the shaft, and our second selection will be any hexagonal side of the hex bearing hole. So once we click apply, you'll notice that the surfaces we selected have been stuck together, I try to move this hex shaft, you'll notice that it only moves in a way that the two surfaces stick together. Now, to fully put this hex shaft into the hex hole, we have to make another mate. Except, the two selections we make must make geometric sense. For instance, if I want to stop this hex shaft from moving, since these two surfaces are already mated, to prevent it from moving up and down like that, we can make a mate between this surface and this bottom surface. And once we click apply, you'll notice that our hex shaft no longer moves. If you take a look at the two mates, we mated these two surfaces as well as these two surfaces. So our hex shaft was mated in two sides so that it would not be able to move around. Let's say I made an incorrect selection. Let's say that I decided to mate this bottom surface with this top surface. Once I click apply, I get a constraint error where the assembly cannot be solved. Let's click cancel. That means that our second constraint, would not work geometrically. Because if we select this top surface, and we wanted to stick to this bottom surface right here, while maintaining the contact between these two surfaces, it wouldn't work out. Whereas if I decided to mate this top surface of the hex shaft with this top surface of the hex hole, it would work out. Because it is possible to have these two surfaces be in contact along with these two surfaces. And you'll notice when I move the hex shaft around, it can go in and out, and while maintaining the alignment of the sides of the hex shaft with the sides of the hex hole. Constraining other items onto the hex shaft is a very similar procedure. Let's go ahead and constrain this lock collar. Our first selection can be any pair of sides. So let's select this inner surface of the lock collar, constrain it to this top surface of the hex shaft, and we'll move it around, and you'll notice that the hex shaft can only move, the lock collar can only move such that these top two surfaces are sticking together or on the same level. Our next constraint will be this lock collar surface, and then this hex shaft surface. Once we click apply, you'll notice that our lock collar can only slide along the hex shaft. Let's go ahead and constrain this wheel. Again, our first pair of sides are any two sides, but our second pair has to be chosen carefully. So let's mate this side of the hex shaft to this side of the wheel's hex hole, which is right there. And once we hear the popping sound, we know that the constraint is good. And finally, let's stick this side of the lock collar to this side of the wheel so that there's no gap. And now our wheel and lock collar slide together on the hex shaft. Another common constraint you'll be using in CAD is constraining stocks together using gussets. When we attach gussets to stock in real life, we use bolts that go through the holes of the gusset and the stock. We can simulate that assembly in CAD by constraining the holes of the gussets and stock so that they line up. So let's go ahead and constrain our first gusset to our first piece of stock. We'll select that hole, and as our constraint, and we'll select it so that the green arrow appears. And then we want that hole to line up with this hole, so we'll make our second selection to be this hole. Now, right now, our gusset is not lined up correctly. So if we play around with the solutions and we select opposed, our gusset will flip in the right direction, and you'll notice how the two axes of the two holes we selected point in opposite directions. So we'll click apply, and we'll move this around so we get a better visualization of the next constraint we need. So each hole on the gusset is spaced ½ an inch apart, while each hole on the stock is spaced 1 inch apart. So our next set of holes will be this hole and this hole. And when we select it, it's right, so the gusset automatically pops into place. And then we can click apply. And then finally, to attach this gusset to this piece of stock, you just need to mate these two surfaces together so that the gusset can't move around at all. Now, let's attach this gusset to this piece of stock. So again, we'll select two sets of holes. So select that one and that one. Click apply. And then for our second selection, we'll select this hole and this hole. And finally, we'll just have the surfaces stick together, so we'll make one final mate with those two surfaces, and we'll click apply. For our second gusset, to make it attach to these pieces of stock like the first gusset, we can first make the holes of this gusset line up with the holes of the other gusset, and make sure to orient it correctly. You select the right solution. In this case, it would be aligned. And then make your second alignment of holes. And finally, constrain the surfaces of the gusset to the stock. And now, the stock and gusset assembly is complete. An important thing to note is that while the width of a stock is 1 inch, the width of a gusset is actually less than 1 inch, as you can see. This means that if I try to use a flush constraint on a gusset and a stock, I might run into errors. So, for instance, if I have this gusset here, and I try to change one of these mates to a flush, I'm going to go ahead and suppress this constraint, which means that I'm basically taking away its function. And I'm going to go ahead and instead try to use a flush constraint on this surface and this surface. If I click apply, you'll notice I run into an error. That's because when a gusset is constrained using holes, it actually centers the gusset, and you'll see that this surface is actually not flush with this surface. So whenever you're constraining gussets with stock, always use a constraint that aligns the holes instead of using flush to flush the surfaces. Because in reality, when the gusset is properly applied by aligning the holes, the surfaces will not line up, they will not be flush. To assemble stocks using short T gussets, the constraining process is almost the same. So we'll go ahead and first select our two holes to line up. Then we'll go ahead and make our second selection. Finally, we'll constrain surfaces with a mate. And then, for our next constraint, we'll select this hole, the one in the middle of the bottom part of the T, and then the last hole on the other stock. And you'll notice that we don't have enough holes on this part of the T gusset to make another aligned set of holes. So instead, we'll just use a mate for this inner surface and this surface of the stock so that they stick together. And when we finally apply this mate, we form our T assembly with our stocks. And just to finish things up, we'll go ahead and align the holes of this gusset with this gusset. constraint here, and then a final mate here. And that's an assembly of 2 stocks with short T-gussets. The only difference between this assembly setup and this assembly is that for this stock to be assembled with this gusset, only one hole is used, and then a mate is applied between the inside of this surface and this surface. Often in CAD, you're going to need a stock of a specific length that's not offered in the parts library of stock that we have. So what you do is you open your parts library, and for the type of stock you need, let's say I need square stock, open the longest length of 59 inches, and then we're going to use the split feature to adjust the length. To do that, we're first going to create a plane, and we're going to select offset from plane, and then we're going to go here and select this square surface of the square stock. And then when it asks for a dimension, let's say that we need a stock that is 8 inches. This stock is currently 59 inches, so we're going to want to cut off 51 inches of stock. So you'll notice that our plane moves up 51 inches in, leaving a 51-inch section and then an 8-inch section. I'm going to click check. Now that our plane is added, we're going to go ahead and use the split tool. And instead of using split face, we're going to select split trim solid. And then for our split tool, we're going to select our plane that we created. And then the arrow points in the direction of the section that you want to remove, but we don't want to remove this 8-inch section. So we're going to switch to the arrow direction by selecting this option. Once we click apply, the 51-inch section of the stock is cut off, leaving an 8-inch section behind. The final thing to do is to hide this work plane. So what we can do is we right-click the work plane on the model browser, and then we select visibility, and once we click it, you'll notice that the check mark goes away and our plane is now hidden. So we have an 8-inch piece of stock left over. An important practice to have when trimming down stock is to maintain something called a factory edge. When stock comes from Vex, the first hole is usually offset from the edge by ½ inch. So whenever you're trimming down stock, always try to maintain that ½ inch offset on both sides, if possible, so that it becomes easier to assemble stock using gussets, which have their holes spaced by ½ inch. Finally, when your stock is finished and trimmed to the right length, go to File and Save As. And typically, for our team, we don't save our modified stock in the parts library because it's not a standard length. So we usually save it wherever our mechanism is. For this example, I'm just going to save it in my downloads, give it a proper name, 1x1 stock, and have the dimension of the stock, the length of the stock, included. So this is an 8-inch stock. So whenever you make a split of a stock and trim it down to a custom length, don't save it in the parts library, just save it where your mechanism is. Another important skill you'll be using in your CADing in FRC is creating a hole in a 1x2 stock for a bearing. So since the stock is divided into these 4 sections, just create a sketch on one of these surfaces. And the important part of putting a bearing hole into a 1x2 stock is having the bearing hole centered. So when you create a circle, you might be tempted to just put the center anywhere on this line, but in reality, you'll notice that this line, if you zoom in, is made up of 3 parts. because the stock actually has a little niche in it, a triangular niche. So when selecting where the center should be, make sure you always have the center along the actual center line. We'll go ahead and make our bearing hole a diameter of 1.125 or 1 1/8 of an inch, because that's the diameter of the bearing. And we'll go ahead and make more specific dimensioning. We'll first check that this is 1 inch off, and that is so. And to offset it from the other edge, we'll do 2 inches for now. We'll go ahead and finish sketch, and then we'll finally finish creating the hole by extruding both halves of the bearing hole. And now that is our bearing hole created. The important thing is to make sure that your hole is centered, again, along this actual center line, and not just choose an arbitrary line that looks like it's in the center when you're in sketch mode. And of course, you can always double check using your measure tool after the hole is created. And that is 1 inch. And finally, similar to how we save our split stock in a folder that's not the parts library, but in a folder with our mechanism, save your stock with the hole in it in a folder where the mechanism is and not in the parts library. And make sure whenever you save it, you give it a name of one. Let's say for this stock, it'll be 1x2 stock, 16-inch with holes. Just make sure that you specify in the file name that there is a hole in the stock. If you head over to vexrobotics.com/VexPro, a lot of the parts you'll be using in FRC can be found and downloaded as step files, which is a type of CAD file. Let's say that we want to acquire a 72-tooth sprocket for 25 chain. We can head over to Motion and Sprockets and Chain, and if we scroll down and select 25 sprockets, which are sprockets for 25 chain, and if you scroll all the way down to the bottom of the page, we get to a section where the rightmost button is CAD files, and if you click that, a bunch of options pop up. And since we want to download a 72-tooth sprocket, let's scroll all the way down, and you'll notice one of the parts is our 72-tooth sprocket. And if you click preview, we can preview the 3D model. And then let's click download. And you'll notice that a step file is downloaded. So now if we head back to Inventor and click open, and we look in our downloads, right now our step file is not visible, but if we click next to files of type, and we scroll all the way down, and instead of selecting Autodesk Inventor files, we click all files, you'll notice that our step file is right there. So let's select that and open it up. When the file opens up and this window pops up, just click OK, and it'll import the part into the Inventor part page. When it finishes loading, your part should pop up. Before we start using this part in any of our assemblies, it's best practice to standardize the color, name, and file type of our part. Let's start with the color. Since this sprocket in real life looks black, I'll select the appearance for this part to be black. Next, let's standardize the file type and file name. So we'll click File, Save As for our part, and head over to the file where we want to save this part to. and we'll give it a name that is detailed about what the part is. So this is a sprocket with a 1 1/8 inch bearing hole. It has 72 teeth, and it is a 25 chain sprocket. So if we go ahead and open the part that we just created, and we open it from the file location we just saved it to, you'll notice it pops up with the right colors, and it already has the right file name, and it is of the right file type, an Inventor IPT. For some step files, converting them to an Inventor file will create an assembly file as well as many IPT files. Let's say we want to download a gearbox. If we head over to VexPro and select gearboxes, and let's say we want to download a versaplanetary gearbox on CAD, we select CAD files, and we'll click a versaplanetary version 2 two-stage 101 gearbox with a bag motor, and we download that. And we head back to Inventor and open up the gearbox. So after the file loads, you'll notice on the model browser that there are a bunch of subfiles, which means that once this step file is converted into an Inventor file, it becomes an assembly along with all the subfiles in the assembly. Let's go ahead and standardize the colors for our gearbox. This will be black. And for this motor, we can open the subfile and standardize the colors further. So since converting our step file into an Inventor file will create an assembly file along with a bunch of part files for all the components that make up the assembly, it's good practice when doing this conversion to create a new folder dedicated just to the created part. So when saving our new converted step file, we'll create a new folder, give it a name, And inside that folder, we'll save our assembly. So if we go ahead and open our file which we just saved, and we open the folder which we saved it to, you'll notice all the part files show up, and the assembly file which we named shows up as well. So let's open the assembly file. And when we open it up, all our changes and standardizations to the colors have been saved. So whenever you're going to use this entire file, assembly file, in another assembly file for your FRC CADing endeavors, just use the file which you named. So if you ever need to use this file for one of your other FRC Inventor assemblies, just use this assembly file which you named.